basically, this session is dedicated to their first stage of IDAO 2020, where there was a task provided by our Lambda Lab and our friends from Italy. And actually, I just saw another task creator joined in. So I guess without any further introduction, we can dive to the session. Aziz, would you like to add anything?
Yeah, I actually would like to congratulate the teams who won the competition. It was a fairly challenging task, but you succeeded. So congratulations. Now describe how did you solve this task?
So yeah, actually we had a couple of teams that agreed to share their tasks for today. And first of all, I would like to pass the word to the team called MN Team 2. I saw you guys over here. So yeah, hi there.
Hello. Hi there.
Hi there. Pleasure to meet you. I can ask a quick question before we dive into the team. MN stands for Mongolia, I guess.
Yes,
Yeah.
our team from Mongolia.
Wonderful. Because I was always wondering. So you have double affiliation with Korea too. So I mean in the registration. So that's why I asked. So please, it's your time, your stage. So we are really thrilled to learn your solution.
Yeah. Okay, I'll introduce my solution. Yeah. Can you see my screen?
Sure.
Yeah. Okay. We prepared a very short presentation for our solution. Yeah. And the outline of our presentation. First, we will introduce our team very shortly and some introduction of the task. We'll give about some introduction of the task and what was our objective and what was our solution, and we'll give a little summary end of the presentation. And our team from Mongolia, and we have 3 members. And my name is Lagwa Dorj Muktalai. Shortly, you can call me Hagi, and I am PhD student at Chumbuk National University in South Korea. And another one of our team member is Altang Ulti Cholong. He is a data analyst at the MCS Group. MCS Group is one of the biggest group in Mongolia. And another one of team name is Chosun Mekmar. He is also a data analyst, and he works in MIG insurance company. It's also one of the biggest insurance company in Mongolia. And our major is actually economics, and we are studying by ourselves some data analysis and something. And then the task for the first stage was image processing, and we can say the image classification and image evaluation. And here is image, and we need to classify this image into 2 class, ER or NR, and we also need to predict some energy level of this image, and that's consists of 6 numbers. Here is a label of the evaluation tasks, and the problem was we thought it was a supervised learning, but actually unsupervised learning methods works better. When I see some approaches for other teams, they all perform very better than us. Then I think it was maybe unsupervised learning approach works better than supervised learning. And we use supervised learning methods. Then problem was a data leakage problem, which is the training set is different from the test set, and our model can be easily overfitted. Then our objective is first we just try to use simple CNN models, and it works well on the both tasks, relation and classification tasks. But when we validate the test data, we have only 9 images from the test data, but it doesn't work. Then our objective was we won't be overfitted, and we changed our strategy. Instead of just training simple CNN models. And first, we have training data set. Here is the framework of our solution. And first, we have training set, and also we have test sample. It consists of 9 images. And based on this test set, we validate our training model. When we train this model, we put our whole training set into the model, and we validate our model based on these 9 images only. And since simple CNN models work well, we just select the mobile net architecture, and we train this mobile net architecture, and we select the best model on these 9 images. Then we use the pseudo, we make pseudo labeling based on the test dataset, but public test dataset, but we just select the 20% of the test dataset, which is the two tail of the labels, classification labels and relation labels. Then we made the pseudo labels for the public training test datasets, and we concatenated this public test dataset and training set, which is our training whole training dataset now. And just we use k-fold cross-validation method, and we train k models based on the same architecture with the previous model, mobile net architecture. And after that, we just predict our model, and our solution was only this. We use some pseudo labeling method, and when we train our pseudo labeling model, we validate our model on the 9 images only, and our KID is just this. And there is some difference. When we train pseudo labeling model, we use bigger center crop images because it was better than smaller center crop. After that, we train the prediction model. We use a smaller center crop of the image. It's 64 multiplied by 64, the sizes, and it was give us some better predictive score performance. Then also we perform some post processing. For example, if class label equal to 0, we just give some thresholds, and based on these thresholds, we make a prediction result of the regression into some labels, constant labels. And the end of this presentation, since this dataset is very different from the training set, CV and LP scores can't represent the model predictive ability, and I think that 9 images are the good choice for validating the model. And we considered on the supervised learning approach, and we also tried to perform some one-shot learning methods such as matching networks, because we have very few number of the test dataset, but it required a very large computation power, and we couldn't perform it. And I think maybe siens neural network may works well on this task, because it looks like a supervised learning model. And thank you for your attention. It's the end of my.
I have a question for you. In the very last point in the summary, it's written Siemens neural network. You mean Siamese?
Yes, Siemens. Yes.
Yeah, okay.
Science, yeah.
Okay. Thank you.
Yeah. Thank you.
So if any other teams have questions, please ask away. Or any other suggestions or whatever, basically. So this session is mainly about discussion and chatting and talking rather than monologues. So please dive in, switch on your microphones, videos, or I don't know if you have anything else to ask at. Don't be shy.
Hello, it's Giulia.
Ciao, Giulia.
Hello.
Ciao.
Pleasure to see you again.
Hi. Now I have a question, but I'm not an expert at all about this neural network stuff. But I was wondering which was the outcome of these of your work. I remember that you you should have a figure of merit of the classification. No. What's
output of our model? Yes.
So maybe I'm not sure how finally the task was prepared by Aziz and the other.
Do you mean like the score or?
Yeah, the score. I was just asking about
score.
the score. Mm-hmm.
Yeah, our fruit word on the score on the fruit word was around 670. Or yeah.
Okay, but
is it right?
Okay, did you try different methods? Did you have the comparison between the scores of the different methods and how?
No, because when we trained our model, the time we have on the training data set, and usually it's going to be outfitted very easily because we got a very high score on the part of the training set, validation set, and then it's very hard to validate our model on the training set. And we know that the test set is different from the training set, and therefore we use only when we validate our model, we use only 9 images. That's given us, and that time our score was it's around 600. Yeah, we predict the 7 images of the 9 images. Yeah, it's almost similar with the probability score. It was. Yeah.
And what was your area under the curve on the MIE loss?
It's around 1, and our error mostly on the relation task. Classification task is when for classification task, we train the different models for the classification task and the relation task. And for classification task, I think there is no data leakage problem. And only in relation task, that problem has been occurred. Then we just leave the result of the classification, and we make we get some probability of the class, and we made it into binary. Then we after divide the binary labels, and we can perform our post processing on the each label. And we just our classification performance almost around 1, and we believe that. Then we make post processing on the relation task. Yeah, then our errors on mostly on the relation task.
Okay, thanks.
Yeah.
So any other questions? In the chat, nothing. In the voice, neither. Okay, so maybe we
thank you.
move on. Thanks a lot. And okay, up next, let me check. So I saw another team. Okay, I saw in the chat Kirill Rybkin from that Sense team. So Kirill, would you join us in?
Okay, hello, hi everyone.
Hi there.
Yeah, sorry, I will be without webcams. Yeah.
No worries. We're all shy sometimes. So I'm giving up the stage to you. So yeah.
Yeah, track one. Okay. Could I start a screen demonstration now? Okay.
Yeah, I just made it a co-organizer, so you should be able to.
Okay. My name is Kirill Rybkin. I'm a member of a data science team. Our team made a very unusual and interesting solution, which I will tell you about now. As you may remember, the task was to predict the classes of particles on image. As you may remember, the task was to predict the classes of particles on image. First of all, I made the assumption that the types of particles' energy strongly affect the total brightness of spots. This assumption turned out to be absolutely correct. If you take an image of spot, subtract the average noise value from it, and sum it pixel by pixel, you can get a very good separation of particles by energy, even without additional features. Those bright sum features was obtained. The slide shows the histogram of 3 energy classes and 2 types of particles. It's enough to set the threshold and the energy classifier is ready. But the classification of the kind of particles still is a problem. Then I made the assumption that the spots are formed from several thousand points, photons, whose position is determined by a random distribution. The points are added pixel by pixel and form spots. It may seem that the image with error 10, 20, and 30 have a different nature, but in real, it's just a spot which is smashed across the track. However, the tracks still need to be detected somehow. To do this, I made a circle rate metric, which determined what percent of bright pixels are inside the center circle. If the statement that the spots are formed by random distribution is correct, then most of the data is noise, and the real significant information is the characteristic of the spots, which depend on distribution parameters. One of those characteristics is a decrease in the brightness of the spot from center to the edge. To determine it, I cut the spots into the circles, for each of which I calculate an average pixel value. So I got something in the form of a topographic elevation map, but only in the form of a graph. The slide shows an example of a plot of hugest of 2 different types of spots. The values is normalized. This is done because the information about the maximum huge is large noise. In order to reduce a number of features, we use a kurtosis coefficient and got one feature instead of 20. So the hugest mass features was obtained. So there are only 3 main features: bright sum, circle rate, and hugest map. In the final solution, we use only these features. Let's return to the problem of detecting particle with the drug. In this graph, shows dependence between features like bright of sum and circle rate. The color shows type of the particles. Adding threshold make it easy to highlight particles with the drugs. Highlight particles with the drugs are in the upper left corner of the graph. As a final model, I use a cut boost to classify image by particle type and threshold to classify by energy. Since the data of public and private was different, I don't add public data prediction to the model, and it wasn't the best solution. I mix up the label classes of particles of types and model prediction the type of particle in reverse. According to the AUG was 0.06. However, the energy classifier was correct, and we have average absolute error around 0.07, so the final result was not too bad. We got the result on the leaderboard, private minus 38, and took the 7th place. Without this error, our result would have been around 900, and we could have taken 2nd or 3rd place. In the end, I would like to express my gratitude to the organizer for an excellent task. It was really interesting for me to solve this problem. Thank you.
Interesting solution. I have one question. What is the circular ratio?
Yeah, of course. 1 second. Okay, here I think it's the best place to explain it. No, okay, here. Look, we have 2 types of particles. First of all is a circle particles, particle image, and it's simple to, and we need some feature which will depend is it a particle with a track or without. So what how does this feature work? I made 20 circles, which 3 of them shows on this picture. It's a mask which multiply with an original image, and we received 20 multiplication operation result. Just image that you multiply this mask on this image. Then I just calculate an average value and receive something like huge, something like a huge, huge map.
By multiplication, you mean dot product?
Yeah. Okay. It's just it's a bitmap. It's just here is the zeros. Here is the ones. Just it's a mask. It's a mask.
Okay.
So we will receive some result with some result image. Okay.
I still didn't get the ratio. Where is the ratio? So you take your mask, put it on the image, you will get a masked image, which represent bunch of pixels. You divide on what?
Okay, look. What do I need? We need to calculate how fast the brights is fall down from the center to the edge. How we can do it if we think that that particle have a circle form? We just draft. I don't know. Can you see my mouse cursor?
Yeah, I do.
Okay, cool. Yeah, and we just draft a circle here and calculate average value of particles of pixel. Just only pixel which in this circle, only pixel, and so we will receive this graph. After normalization, it will look like this. It's like how fast does average value fell down from the center to the edge.
It would be great if you could translate the Russian axes, because not all of us speak in Russian.
Okay, I'm sorry.
Yeah, so what is the x-axis and the y-axis and...
Here on this picture.
Yeah.
I'm sorry. I understand now. I just didn't have data of. Okay, sorry. On this graph, we have it's a distance from a center of picture, just 0.1.3 and etc. And here it's a average bright on this range. It's just yeah, I'm sorry, I can't.
It's fine, I understood you, yeah. On the graph on the right is basically like the brightness distribution with respect to the distance from the center?
Yes, exactly. Yeah. And then we calculate one feature from this graph. And that's it. And yes, it's a feature Hughes map.
Yeah, I see. Interesting.
Yeah, on this graph, I think it's too small to read. It's a graph shows a circle rate and bright sum. It's just how to explain. It shows. Okay, look here. We have particles with a small energy. Some particles has so small energy that it's distribute, and my feature circle rate just doesn't work, and it's too bad. But some of them enough, right? And they have a good circle rate score. And here it's particles with higher average energy, and it's possible to use a threshold here to classify them. As you can see, it's colors here. It's a true value. So as you can see, particles with a green color mark only place only right from this threshold line.
Yes. And the bright sum is basically the summation of the masked pixels.
Sorry, what? Can you repeat?
The bright sum, like as far as I can tell, this is basically you take the masked image and you sum the mass?
Yeah, it's just sum of a pixel minus some noise, average value of noise, and we receive a really good value of a bright sum. Yeah, of course, for bright sum, we cut off our image by center. As you can see, it's example of this view.
Mm-hmm. Okay, I see. It's nice.
Thanks a lot for your wonderful presentation. Maybe anyone else has questions to Kirill? So basically you can write to the chat box, or we can switch on the microphone. Okay. Giulia, maybe you have any questions?
Okay. Can you go to the next slide? Just to be sure that I understood. The next slide. The next, or maybe should be the next, the one with the circular ratio. Yes, this one. So I didn't understand the green and blue points correspond to different particle types.
Yes, it's a type of particles. It's ER or NR. Just
and the ER are the
okay, 1 second. The tracks with it's ER. So blue it's ER, green it's NR. As you can see, blue have a really small circle. Blue particles have too small circle rate when they have big energies. It's because
because
they have a long track, and it's easily to classify them with just a simple threshold here. But some particles with a small energy have a lot of noise, and this metric circle rate just doesn't work because too lot of noise, and this so we didn't use this threshold with too small energy particles.
Okay.
Thanks. Anyone else? Actually, I see another person involved in task creation in the chart, Nikita Kazeev. Nikita, maybe you have anything else to add, ask, or? I think Nikita is not with us, by anyway.
Okay, I have one more question. How many circular masks did you use?
Around 20. It's yeah. In real, I forgot, but yes, around 20.
Mm-hmm. Okay.
Yeah, as you can see on this graph, it's from 0 to 14. So yeah.
Yeah, I see.
Yeah, but it started not from a zero, but we start from around radius around 3 or 4 pixels, because 1 pixel it's nothing. It's not statistics.
Yeah.
Okay. So I guess there are no additional questions so far. Thanks a lot, Kirill, for presenting your solution. And hope that you enjoyed the overall competition and the final two. So yeah. So basically, if anyone else, I guess anyone else from the chat could randomly contribute to the discussion. So since there are some other participants, if you like to share some interesting ideas, features, or anything else to their to the discussion. So doesn't seem so. Okay. So in this case, maybe you have any questions to task creators, since they are all here in the full set. I think it's a nice opportunity for you to interact with them. Maybe you have like questions not necessarily on machine learning part, but more on the part of physics. So since our colleagues are also here in the chat, it's also a wonderful opportunity to ask them.
Yeah, maybe I have one question to organizers.
Sure.
Yeah. Okay. If it was did you generate this image with a real physical process, or just use some random distribution? Because when I check, it was too similar to normal distribution. Just, I don't know, it's look like maybe just the process in the physics or works the same way, but I don't know.
Okay, maybe I can try to answer. So the fact is that actually it's similar to a normal distribution, just because I don't know if you were present when I presented the physical part of the task, but then when you have the interaction of a particle in this detector, then there is a process that basically diffuses the image. You have a single point of interaction becomes a Gaussian spot. So if the track is very short, in the end, the Gaussian diffusion is larger than the actual length of the track. So in the end, you got a normal distribution. If you have a very long track, then there is like there are many spots. Each of them becomes round, but if the track is long enough, then you will still see some long track instead of a single spot. I don't know if I
thank you.
Explain.
Yeah, and I understand. And maybe one more question: if it was a random noise, real random, maybe it was some dependence, because, for example, we use one more feature. I didn't show it in the presentation. We calculate average value of pixel under the point and up to the point, and this average value a bit correlate with the pixel on this split. It's look like there is a correlation between between a pixel by one line.
So it's the random the noise that is below the image is random, but it's electronic noise of of a sensor, of a camera sensor. So in real world, you can have some pixels that are systematically higher than the others. So you can have some pixels that in all the images are actually are not really random. They have some correlation.
So, okay. Yeah, thank you.
And also, if I can add something, Julia, to it, the noise which is seen in these images are CMOS sensor noise, and we take the images in very low lightning condition. So there's a fixed pattern noise, which you were saying that we see noise, the particular row is higher than the adjacent rows. That is called fixed pattern noise, and that is very prominent in the CMOS sensor at very low illumination condition.
So it seems that, so anyone else who wants to contribute? Since we all...
I have just a comment. I don't know if it's just my impression, but I had the impression that the second approach was, the second team was more similar to what we actually do for the analysis, because we, for example, the approach of summing the excellency when the brightness of the the brightness of the drugs, and classify and find the energy as the brightness of the drug, actually. So I found it more visual approach. I don't know how to say. Well, the first one, if I understood, because I'm not sure I completely understood, but it looks to me more abstract approach to the images, more just like numbers, and find correlations among these basically matrix of numbers. And yeah, it's interesting.
Yeah, I mean, but anyway, I think it's good to hear that there are some completely opposite solutions, I guess. So if there are any other questions or contribution to the discussion, of course, you are always welcome to contact any of us. And so I would like to have additional chance to thank our Italian partners from CYGNO collaboration for helping us with the task and data, and Lambda Lab for, again, setting the task too. So yeah, I guess you all had great fun with that.